Hello everyone. So in this session we are going to start our discussion for floating point representation. So whatever the numbers we have discussed so far for addition, subtraction, multiplication, division are considered only for integers. That means the point is fixed in the right extreme. Okay, now we are going to discuss about the need for floating point and how the floating point numbers are going to be stored inside the computers for processing, and how the computer's arithmetic logic unit is able to process this floating point numbers that we will discuss today. Here, what is the need for floating point numbers? Okay, so when we are just representing the numbers, it can be too large or it can be too small. For example, if it is going to be a pi value, it is represented as 3.1415 like this. The fraction part is going to extend along. Okay, and similarly, if you take the exponent value, the value of e is 2.71828, and then so many numbers are to be represented for this after this point. So the number before the left, to the left of this decimal point or the binary point, it will be called as integer, and the one to the right is going to be called as a fraction. Why we use fraction is the purpose of having the fraction is to represent too small number or too huge number. For example, if I want to represent the time in seconds or in nanosecond, see here, if you just see this example, it is 0.0000, so many fraction digits are there. Maybe to cut short this, we can represent that in the form of this notation like this. So I am just bringing the point from the left extreme to this point 1.0 into, so here 0.0001, it is a too small number. I am trying to make it as a bigger number 1.0. So that has to be adjusted only in the exponent by appropriate number of positions which we have moved towards right. So the point in this position has been shifted to 1, 2, 3, 4, 5, 6, 7, 8, 9 digits to the right. So when I move the point 9 digits to the right, we are trying to increase the magnitude so that you are compensating by multiplying that number with 10 raised power minus 9. So how many bits you have shifted towards the right, that many number will be raised as a negative power. So you can represent this very small number in the form of this notation like 1.0 into 10 power minus 9. So if you see this number, this is called as the scientific notation. So very small numbers or very large numbers are going to be represented in the scientific notation form. So in the scientific notation form, we are having the decimal digit 1 digit dot, then we have so many fractions into 10 raised power exponent. So we have the decimal digit, okay, integer portion, and then the fraction part, then multiply with 10 raised power e is nothing but exponent, and this e can be plus or minus. So you can have plus number for a very large number, and we can have negative number to represent very small number. Okay, so now this is going to be the example of the floating point numbers which is represented in base 10. So 5.341 into 10 power 3. Okay, so how actually we will convert this number? So we will multiply this number with 1 followed with 3 zeros. If we have 3 zeros following here, then that can be cut short and it can be raised to the exponent as a positive power. So here we have the decimal point because it deals with the decimal number system, and we have this d, that d is nothing but the integer portion, f as the fraction portion, and this is the base. We are dealing with the base 10, so it is base 10, and the exponent is e, that is minus 3 here. Now how the floating point numbers are going to be represented in base 2 notation. So these are the some of the examples of floating point numbers represented in base 2. Instead of decimal point, here we will call this point as a binary point because it is a binary number system. And important concept with respect to floating point numbers is that as far as the computer arithmetic is concerned, it will expect the floating point numbers to be in the normalized form. So we have the concept of normalization. What actually we mean by normalization? That means exactly one non-zero digit should appear before the point. Okay. So now maybe if we just discuss the example, then it will be clear. If you just see this example, 5.341 into 10 power 3, you just observe the position of the decimal point here. It is exactly after one digit. So if the decimal point is exactly after one digit, and if this digit is not zero, if it is a non-zero number, then we say that the number is normalized. Again, in this example here, It is a binary number system, so we have the binary point exactly after one digit to the right, okay, and this digit is not 0, then this number is said to be normalized. Okay, now we will just see an example for unnormalized number. Here we have point 0.05. Okay, to the left of this point we have a 0. If it is going to be non-zero, only then it is called as a normalized number. Similarly, in this example also, to the left of this point there should be only one digit, and that one digit should be non-zero, but here we have multiple digits, we have 4 digits, so this number is not normalized. Maybe in the next slide we will just see how to normalize these two numbers. Okay, maybe we can take this example, and then we will just see how this number can be normalized. So if we just see this example here, we have observed that the point is not to the left of the non-zero digit. So if I want to normalize this number, what should I do? So I will write the number like this. So 5, 3, 4, 1. Okay, that means I'm just trying to move this point to the non-zero digit. So I just move the point here. Okay, it is 5.341. I'm just going to write like this. So already the exponent is 10 power 5. Okay, now earlier the value is 0.05 something. Now I change the number as 5.3. That means I have increased the magnitude of this number. If I increase the magnitude of this number, then it has to be compensated by decreasing the exponent power. How should I adjust? So how many digits I move towards right? 1, 2. So 2 digits I moved right. The point has been moved towards right by 2 digits. So that many number has to be subtracted from the exponent. So I have to subtract here 10 minus 5, sorry, 5 minus 2. So now how the number is going to be represented now? It is nothing but 5.341. So the point in this position has been moved such a way that to the left of this point we expect one non-zero digit. If there is only one non-zero digit to the left of this point, then this number is said to be normalized. In order, since we have changed the number from this form to this form, we are adjusting that by appropriately adjusting the exponent. So now the exponent will become, earlier it was 10 power 5, 10 power 5, now it become 10 power 5 minus 2, so it is going to be 10 power 3. So the value is going to be the same. Now we have normalized this number 5.341 into 10 power 3. This is going to be the normalized representation. Similarly, if we take this example, here the number is not normalized. Let me write this number. The original number is minus 1101.101 into 2 power minus 6. So it is not normalized because to the left of this point we have multiple digits. So as per the definition, there should be only one non-zero digit. Only one non-zero digit. So that means we have to move the point to this position. So only then we'll be having only one non-zero digit. So it should be like this 1.101101 into 2 power. So from this position we have moved the point here. That means the original magnitude, the original number is 1101 point something. Now we have changed the number as 1 point. That means we have reduced the magnitude. We have reduced the value of the magnitude. So that has to be compensated by incrementing the exponent. Okay, already it is minus 6. Now I have to add to that many number how many bits I have moved towards left. So 1, 2, 3. 3 digits I have moved towards left. So minus 6 plus 3, it is going to be minus 3. So the normalized number is going to be written like this. It is 1.101101 into 2 power minus 3. So this is going to be the normalized number. So we have just seen the floating point numbers, and we will check the position of the point. If the point is immediately after one non-zero digit, then it is called normalized. Here number is not normalized. We are trying to normalize. To normalize, we move the point either towards left or right. Accordingly, we adjust the exponent by incrementing or decrementing. So these two numbers are good example for unnormalized number. One in the decimal number system, another one in the binary number system. We have just changed these numbers into a normalized form like this. Okay. Okay, now we will discuss how these floating point numbers are going to be represented by triplet. Okay, so any floating point representation will have three components. One is called as the sign component, another one is the exponent, and then the fraction. So S is going to be the sign bit, and the sign bit can be 0 for positive numbers and 1 for negative numbers. So this is representation is usually, I think we have already discussed as the signed magnitude representation. So we will just have the sign for the exponent, okay, for the fraction part. and then we have the second component as the exponent. E is going to be called as the exponent field, and the exponent field normally we will have sign for the exponent field. So very large numbers will have positive exponent and very small number will have the negative exponents. Okay, and the number of bits in the exponent field will increases as the range of value will increase. That is going to increase. Now f is the third component, which is nothing but the fraction field, and whatever we have after the binary point, that is going to be called as a fraction field, and the number of bits in the fraction field is going to be decided by the precision. So generally the value of any floating point number, if it is represented like this, it will be calculated like this. So we will just have this exponent, that is nothing but 2 raised to power value of the exponent. Okay, and this has to be multiply with what, with the value of the fraction whatever we have given here. Okay, and of course we have the sign, and this sign is going to be attached only for the fraction part. So this has to be multiplied with minus 1 power s. Okay, so this is going to be the actual value. So given the three fields like this, we will find the floating point value by substituting the values in this. So s is going to be attached to the fraction, and whatever is the value of the fraction that will be considered here, that will be multiplied with 2, because it is binary number system, 2 raised to power value of e. Now for the normalized floating point numbers, as we all know, we have three components in the floating point representation. One is the sign, exponent, and the fraction. So this will be the format given. And now what will be the value that is going to be considered? So we have the sign that is not going to be disturbed, and the fraction part we have f1, f2, f3, f4. So this fraction part is going to be decided only after the decimal point, after the binary point. So there will be always a 1, because we told that in our number to be normalized, there should be one non-zero digit to the left of the point. Because this binary number system, it is always going to be 1. So this 1 point, this number is not going to be stored inside the computers. It is always understood, and during the calculation it will be substituting the value 1 here, and then whatever the fraction number we have represented here, so that will be considered as f. Okay, and then this will be considered for base 2. So the significant is going to be considered as 1 point f. Even if we give only f, this 1 point will be taken for substitution, because in floating point representation we always expect the number to be normalized. So the hidden, this normalized number 1 is always not stored, and significant, and because of this the significant is always 1 bit longer than the fraction. We are not going to use any memory space for storing this one, because it is implied. So if you take any value of the normalized floating point number, it is nothing but minus 1 raised power s, this is the sign bit, into the fraction we have f1, f2, f3, f4. So that we will be writing down, and you will be writing down the hidden one, because this one is not represented here. We already know the number is normalized. So to the left of the point there will be one non-zero digit, which is nothing but 1, and that will be multiplied with 2 power exponent. So whatever is the exponent, that will be substituted here. So the same thing, it is just given like this, minus 1 power s into, and this 1 will be taken as a integer portion plus, and whatever the fraction we have, that fraction part is going to be considered into its equivalent binary value, then multiplied with 2 raised power value of the exponent. Okay, so this completes the discussion of the floating point number representation, and we will further continue with some more examples of how to handle with the floating point numbers. So the significant s, the significant s is nothing but this f. Okay, and this e is otherwise referred as the exponent.